I'm going to introduce Jing Feng, who is a postdoctoral research associate in the Atmospheric and Oceanic Science program of GFDL, which is at Princeton. She currently works with David Painter, and she has been recently working on the very impressive feat of updating the radiation scheme in the GFDL ESM. So I think that's very cool. Prior to joining GFDL, Jing received her PhD in Atmospheric and Oceanic Sciences from McGill University, where she studied the impacts of convection on upper-tropospheric and lower stratospheric water vapor. So please join me in welcoming Jing.
Thank you so much for a very nice introduction. So a little bit more about my background. So during my PhD study, I'm a satellite retrieval person. I developed all-sky retrieval scheme using satellite instrument on board ATRAS constellation. And now at GFDL, I'm more interested in improving the cloud radiation interaction and the climate model of GFDL. But then today my talk is really about the more idealized scenario, and I wanted to show how well we could understand the outgoing long-wave radiation in a clear sky condition and how does that implies for the climate radiative feedback. So I would like to thank the contribution from my co-author, David Painter, Raymond Menzel, and Changong Wan. So this is a simple schematic plot that shows the Earth's energy budget. So Earth receives the energy from the sun in the solar spectrum, and it turns energy back to space in the form of infrared radiation in the long wave. So at an energy equilibrium state of the climate, the two would perfectly balance each other, but it's not really the case in the reality. So if the OLR is smaller than the solar incoming radiation at the TOA, then there is extra heat in the climate system. And in order to get rid of that extra heat, the climate has to warm, and then the OLR has a significant impact on the Earth's energy budget and the climate system. So here is a figure showing how the multi-year mean clear sky OLR is distributed with surface temperature from the reanalysis model. So here I'm taking ERA5, and each dot in this plot represents a grid point on Earth. And I'm taking the monthly mean, the multi-year mean of that. So if it's more green, it means there's few grids that fall within the certain range, and if it's more yellow, it means there are lots of grid points that fall into the surface temperature range. So you can see there's the grids become denser and denser once reaching like 260 Kelvin temperature range. And the tropical ocean is around like 3 Kelvin. So we have much more scatter once from the cold to the warm regions on Earth. So the black solid curve here is really just used to describe the mean OLR at every surface temperature range. So you can consider it as an area-weighted mean of the scatter plot I'm showing in the background. So what it's describing is quite interesting. So it shows a linear increase of clear sky OLR with surface temperature at a rate around 2 watts per square meter per Kelvin. And then there is a stronger deviation from this linear line in the tropical ocean at around 300 Kelvin. Again, I'm showing a very similar figure, but instead of using ERA5, I'm showing the CIMIC-6 models. So I'm using the same time period from 1998 to 2014, and the same period for AMIP and the ERA5. So the ERA5 data is shown in black curve. It's identical with the previous one. And then each line with a marker on that represents a model from CIMIC-6 ensemble. So I marked this model with the box here. So it falls into a lower range of CIMIC-6 ensemble for the AMIP simulation, and it produced a slight outlier at 302 Kelvin in the tropical worm pool. So yeah, but overall, those models have a really close, a linear increase of OLR with surface temperature that are similar to URA5, and they have similar positions that reach a peak and then a dip in the 302 Kelvin. Those features are similar, but then I also want to point out there's large spreads. Consider I'm comparing the OLR at the same surface temperature range, and the differences among model are up to 15 watts per square meter. So here's again, I'm jumping into what happens if the climate warms. So this is a figure that we take from a recent publication by Zhang and Wu in 2020. So on the top panel, I'm showing the global mean OLR as a function of the global mean surface temperature. So each dot represents one model and 1 year average of the model run. So you can see there's an increase of OLR with the time in the abrupt 4 times CO2 experiment. So this represents the climate warming under the forcing. And very interestingly, if you can see, those models are just parallelized to each other. And the rate that OLR increases with surface temperature, also known as the Longwave climate feedback, is at a very similar magnitude compared to the previous slide. It's around like 2 watts per square meter per Kelvin. And then Zhang and Wu took a look into the tropical mean between 30 south and 30 north. And again, we find a similar rate of OLR increase at 2 watts per square meter per Kelvin. So now, after seeing those figures, I have a few questions in mind, but I think they are not quite well understood in the past. So the first question is that what shapes the near-linear clear sky OLR increase on present-day Earth, and what is the role of atmosphere in this process? The second question is that what caused the non-linearity in clear sky OLR of the tropical ocean that we see here, and what is the cause of the inter-modal spreads? Consider that the sea surface temperature is prescribed in this AMIP simulation, and we are comparing the OLR spread at the same surface temperature range. And if I have enough time to cover it in this talk, I will also say something about what does the clear sky OLR relation observed on present-day Earth imply for the future climate projection. So yeah, let me begin with a more detailed look into what radiative process are controlling the magnitude of OLR. So outgoing long-wave radiation at the top of atmosphere is basically sourced from the thermal emission from the surface and from the atmosphere. So the surface emitted at a rate that controlled by the blackbody thermal emission as a function of the surface temperature. So it's basically theta T to the 4 following a step from Boltzmann's law. And in order to get into the top of the atmosphere, it has to be passed through the atmosphere that contains greenhouse gases, and greenhouse gases are absorbing radiation in the infrared. So it gives us a transmittance of the total atmospheric volume that I denoted as tau over bar here. So the surface contribution to OLR is just the first term that I circulated here. So in the meantime, the atmosphere not just absorb the radiation that emitted from the surface, but it itself are re-radiating thermal radiation back to space. So this term are denoted as OLR-ADN that I marked in blue here. So then it's natural to decompose the rate OLR changes with surface temperature into the two components, one directly from the surface and one from the atmosphere. So the reason why I partitioned into this becomes more apparent in the next slide, but here you can see that the surface contribution to OLR slope is quite symbol is just a partial sensitivity in OLR to the perturbation in surface temperature. It's the magnitude mainly controlled by the tau over bar that represents the atmospheric transmittance across the entire column. And then the atmospheric term is more complex because we attributing any perturbation in the transmission of the atmosphere and the re-emission of the atmosphere into this atmospheric term together. So it's a little complex to be understood. So a simple view to understand the OLR slope is proposed in very early studies and then being constantly revisited and now recently revisited by some more advanced studies. So basically, it's find a way to get rid of the complex atmospheric contribution term. So it says that the emission temperature of water vapor is independent of the surface temperature of this atmosphere. So basically, it suggests that the lambda ADM here is a 0 and that the OLR slope is just dominated by the rate or surface contribution changes to under surface temperature warming. So it relies on 3 key assumptions. So first, the atmosphere is dominated by water vapor and there's no contribution from CO2, CH4, NTO, and ozone. So those are well-mixed greenhouse gases and ozone. And the second assumption is that the atmosphere has fixed relative humidity. So the first 2 assumptions give you constant absorber mass at a given temperature range. And the third assumption is that the extinction efficiency of gas absorber is also a fixed quantity as well. Combining the 3 terms, they get a conclusion that emission temperature, is a constant value, regardless of the whether it's at a cold region or at a warm region. But for those of you who are into radiation, you probably know that this statement are not true. So I will go through in the first part of the talk to show you how this Simpson's rule breaks down and why it breaks down. So first of all, I want to point out that the surface contribution is a very simple term that can be easily calculated using radiative transfer. So the rate blackbody emission changes with surface temperature can be easily derived from the derivative of Stephan-Boltzmann law. And the transmittance of the entire atmosphere can be derived from accurate lambda-line radiative transfer. So here we conduct such an accurate lambda-line radiative transfer using the input from ERA5 and then showing this surface turn in the figure on the right. So each box represents a grid point on Earth, similar to our the first figure that I showed in the beginning of this talk. So you can see that the magnitude of this surface turn is generally under 1.5 watts per square meter per Kelvin, and it's much lower than the 2 watts per square meter per Kelvin that we see in previous slide that controls the rate OLR increase of surface temperature. What controls the magnitude of the surface term is really the transmittance through the entire column, because if you took a given surface temperature range, say at 280 Kelvin, the rate blackbody emission change with surface temperature is given in theory, and what the only Byron term is the transmittance. And then think about that the greenhouse gases such as CO2 and methane are well mixed. It means that at every column it has the same amount. Then the major varying term becomes water vapor, because the moisture atmosphere can host more, the warmer atmosphere can host higher moisture content, which gives you stronger opacity in the infrared. So you can see that this red curve that describing the mean of the scatter plot I'm showing here is decreasing once it's in the tropical, really because the tropical air is allowed to hold much more moisture, and that decreases the opacity of the atmosphere, increased opacity of the atmosphere, and the atmosphere becomes completely opaque if the lines continue with the warming, and then that gives an almost zero surface contribution in the warm tropical regions. So if we integrate from here over the surface temperature, we can have an estimate of how much Simpson's law can explain the OLR change from cold to warm regions on Earth using the surface contribution. So the the red curve on this figure is just the integral of the previous figure over the x-axis at the surface temperature. So you see this black curve again, it increased at the rate of 2 watts per square meter per Kelvin, but then the estimate given by Simpson's law is only 1.2. So the big differences between this black and red curve clearly suggest that Simpson's law doesn't strictly hold in reality, and that the atmospheric contribution to OLR when surface temperature increase is definitely not a zero number. Oh, I think I go into the end of the talk rather than so I accidentally hit the end.
Oh.
Right. So I was on this one, and now, right. So we can now separate the atmospheric contribution from our radiative transfer calculations. So this time we really focus on the region that are warmer at 270 Kelvin, because from the density scatter, you can clearly see that most of the grid points fall within the warmer side of the Earth, particularly over the tropical ocean. And there's nothing too special about the OLR-Ts relation and in the colder part of this plot. So one thing we do here is that we calculate how much OLR increases with respect to a reference point at 270 Kelvin, and then you can see the top panel in black curve as just a change of OLR with respect to 270, but start from the zero axis here. And the red curve is moving upwards of this red curve that you're showing here, and it's an integration of surface contribution following Simpson's law, and we see what it can give us. So, and the differences between the black and red give us the atmospheric contribution, and I show it in the bottom. So clearly you can see that the surface contribution accounts for 60% of the linear increase in the OLR relationship, and the atmosphere accounts around 40% of the slope, and also controls the shape of the OLR in here. So that's a direct evidence that Simpson's law doesn't hold in reality again. Let's examine the assumption that made in Simpson's law and see how it breaks down in the reality of Earth's atmosphere. So again, these plots on the left are the same as the previous one, and one thing we do is follow in the assumption and remove CO2, CH4, N2O, and ozone, basically all other greenhouse gases other than water vapor, but then keep the background gases such as nitrogen and oxygen so that the atmosphere mass doesn't break down. So we run the rate of transfer with identical temperature and humidity inputs, but just removing those greenhouse gases, and see how the surface turn and the atmospheric turn looks like in the solid dots that I show in the plot on the right. So removing other greenhouse gases definitely changes the opacity of the atmosphere, because now we have less greenhouse gases and the atmosphere becomes more transparent, so that the surface term in red kind of increases compared to the reality. But one thing that's really important here is that the magnitude of atmospheric term in blue remains very similar to the reality. So it means that it's not really the first assumption made in here that breaks down Simpson's law. And indeed, the emission of the atmosphere is mainly controlled by water vapor. So in that, Simpson's law is true. So we can safely keep other greenhouse gases in our follow-up calculation in the rate of transfer. So now let's look into the other two assumptions. So one is about the fixed RH and the other is about the fixed extinction efficiency per mass. So Simpson's law expects that if you integrate the water vapor from the TOA to a specific atmospheric temperature layer, you will always hit the same water vapor mass at identical air temperature levels, because the relative humidity of the atmosphere is the same. So here on the left, I'm showing the integrated water vapor path to TOA. The x-axis is surface temperature, and y-axis is air temperature. And this is it's not a reality, is what the Simpson's law assumes using the relative, a constant relative humidity. So you see this curve is flat, which means that, if the water vapor mass is indeed under some assumption, it can be irrelevant with how cold and how warm the surface temperature is. And then, if we combine the assumption in Simpson's law that assume the extinction efficiency is a constant value too, then we can just times this figure on the left with a constant coefficient, and then we will get a transmittance through water vapor on the left. And that should be a flat line too. And then in this case, Simpson's law would hold. So just following this idea, we can run a rate of transfer through an atmosphere with constant RH and test it whether it's true. Right? So this is exactly what we do here. So how should I
think if you just click away from it, it might go away.
Oh, yeah, nice. Yeah, because it's kind of important for me to show the title. So this is what I do here, that fix the tropospheric relative humidity at every layer and every column perfectly at 60%. But then at the same time, I constrain the column integrated water vapor as the same as in RA5, and this is done really by removing or putting extra amount of water vapor in the near surface layer, so that in this case we can, because column integrated water vapor is the controller of the transmittance. So in this case, we can get an identical surface contribution as we see in ERA5. So, and this is exactly what you see here by the overlapping red colors here. And then the atmospheric contribution with RH held fixed at 60% as shown in the blue here. And this is not zero, which means that the assumption or the conclusion of Simpson's law that emission temperature does not change with the surface temperature does not really hold in this idealized case with fixed RH. So why does that occur? So again, we have to go back to this view of integrated water vapor path with x-axis being surface temperature and y-axis being the air temperature. If we plot this figure on the left in a more conventional coordinate using air pressure in the y-axis, then, because the air pressure tends to be fixed at 1,100 Pascal, regardless whether it's in the colder or the warmer region on Earth, then you will see this flat contour curve on the fixed RH to be shifted upwards to a lower air pressure and higher altitude range. So it means that the same amount of water vapor mass in warm regions tends to be heated by less abundant background gas such as nitrogen and oxygen. And we know that nitrogen and oxygen contributes like the majority of the atmosphere in Earth. So that means the less frequent collision between water vapor molecules and those background gases decreases the opacity of water vapor. So water vapor becomes less absorbing to infrared radiation in this case. And then, transferring to the words that Simpson used as the extinction efficiency of the same water vapor mass becomes smaller at a warmer surface temperature range. So then we run the actual radiative transfer calculation and see how does that decreasing extinction efficiency affects to the transmittance. And we can see this B plot from the actual radiative transfer. So what Simpson expect as the flat curve again, showing the red curve, showing the red line, and then the actual transmittance is from the purple, and it's kind of sinking down from cold to warm regions. So it means that the emission temperature in warm regions tends to be located at warmer air temperature levels, so that when the emission temperature of the entire atmosphere increase, we will also have more emission from the OLR that can be from the atmosphere that escape to the top of the atmosphere. Or in other words, the atmospheric contribution to OLR increases with surface warming. And one thing interesting here is that, so this line of transmittance increase tends to follow a linear increase trend. And in one of our recent paper, we show that when considering the spectroscopy of water vapor, we can analytically show that emission temperature increases at a rate controlled by the coefficient beta here, and it's really controlled by the spectral overlap between water vapor and other greenhouse gases in the atmosphere, and it's kind of dependent on the spectral absorption channels that we are expecting. So for those of you who are interested in the detail, please you can find a recent publication in JTR. So if we go back to like why the atmospheric OLR tends to be linear with surface temperature, now we have an answer. So with the fixed relative humidity that following Simpson's law, we have a near linear increase of OLR with surface temperature, and this is depicted in the purple solid dot in this plot. So this shows the actual clear sky OLR from the radiative transfer model following this assumption of fixed RH. And why it appears linear as just a simple mass? Because it damps the T to the fourth dependence on the Stefan-Boismol law, and this beta coefficient just dampens the response, so that this curve appears linear in a narrower surface temperature range. So the take-home message on the first section is really about the atmospheric emission. As important as it helps maintain the linear OLR-Ts relationship, and this effect is come from the pressure-broadening effect between water vapor and background gases. And both surface and atmospheric contribution to OLR is highly sensitive to water vapor. So in the second part of the talk, I am more focusing on what's the reality and what's the deviation from the simple linear relationship, because we know that the energy fluxes over tropical ocean and given different time period can be highly variant. So now, like if we draw a box in the over the tropical warm over the warmer area on this plot, like we can see that there's a maximum of OLR tends to be around 298 Kelvin, and that it decreases at until it reaches 302 Kelvin in the tropical warm pool. And you can refer to the plot on the right that shows a multi-year mean surface temperature based on ERA5 from the 1998 to 2014 period. So the gray contour market the tropical area with strong non-linearity that I'm showing here. So this 298 Kelvin corresponds to a drier subtropical ocean, and it's corresponding to a dry descending region. And the minimum on this plot at around 302 Kelvin corresponds to the tropical warm pool, and this is known as the most convective region on Earth, and it's very moist. So one conventional view of like kind of explaining why OER is lower and the warmer moisture side of the ocean than the colder drier side of the ocean is very simple. So they say that like in the moisture region you have more trapping by the atmosphere, so the emission from the surface cannot be effectively emitted to space. So that's why we have a lower OER. So let me show whether this conclusion is correct in a kind of a detailed way. So again, I'm showing this plot with the relative humidity held constant at 60%. But in the meanwhile, I am conserving the column integrated water vapor as it is in the ERA5. So it's just that the humidity is not correctly distributed in the vertical layers of the atmosphere, and the variation only occurs in the bottom of the atmosphere near the surface. And in this case, although we have identical column integrated water vapor mass, as in the reality, we cannot reproduce any of the feature that a peak and a dip and that show in the reality. So it means that the water vapor mass holded by the entire column does not explain any of the non-linearity that we see in reality, and the vertical distribution of humidity must play a very important role here. So here I'm showing the actual surface and atmosphere contribution from ERA5 in solid, and then the idealized scenario with 60% of RH in the dots. Those results you have seen before. And now let's just try to see how the water vapor pass from the COA to the atmosphere layer changes with surface temperature. So you can see that the black curve is the reality, and 60% RH assumption is made here. So you can see that in comparison, the reality, we have much stronger drying in the troposphere when you see that the curve goes down. So it means that, from 270 Kelvin and to around 298 Kelvin, we have a steeper increase of OER, really because the troposphere, particularly upper and middle troposphere, becomes drier. So this gives us a warmer emission temperature as the curve sinking down into a warmer air temperature range. And this warmer emission temperature increases the OER. And why the OER decreases from 298 to 302 Kelvin is really because if you check the contour line in black compared to the flat one, you have a very strong moistening in the middle troposphere that corresponds to around 260 Kelvin. So this is around 500 millibar in the atmosphere. So the dramatic moistening in the from when switching from the subtropical ocean to the tropical warm pool leads to a colder emission temperature of the atmosphere, and that decreases the OAR. So then we do another experiment, like try to restore the actual relative humidity profile seen in the reality, layer by layer from the 60% idealized experiment. So you can see the effect of every layer to the shape of OAR curve. So from the bottom, in the color red, that's the effect from the bottom atmosphere, like starting from 1,000 millibar to 750 millibar, and on the top, I'm calculating the contribution layer by layer from the upper atmosphere. So what is important here is that it's really the vertical range between 250 to 750 hectopascal that's shaping the differences between the actual OAR and the idealized scenario. And it means that the nonlinear OAR and the variation in OAR is mainly shaped by the variation in relative humidity between the 250 and 700 millibar in the mid-troposphere. So since like this vertical range is so important, then we wanted to see how well it can explain the inter-modal spread that I showed you guys earlier in the very beginning of this talk. So this one is slightly different from the beginning of the talk because I wanted to clearly separate how much differences caused by the discrepancy in atmospheric states, like in temperature, humidity, and perhaps the land temperature, and how much differences is caused by the radiation treatment in the model. So here I'm using the same radiative transfer model, RUTMGP. So this is a toolbox developed by Robert Pincus, who is in University of Columbia. I guess you can see him very often. And the input is taken from the AMIP model, AMIP simulation. I use 19 pressure level as the input. So the first figure on the left shows a very similar plot to the one I showed in the beginning of the talk, except that RTMGP is used for every model, and ERA5 for comparison is in black. So it's kind of tends to have a higher OAR compared to other CMIP6 models. And GISS model is again boxed here. It's actually fall well within the different models. I have 24 CMIP6 model here, and the middle panel evaluate the intensity of over OAR non-linearity. So I choose a symbol index as the differences between the 298 to 302 Kelvin range. So this represents the most dramatic humidity changes over from region to region and over the tropical ocean. It also represents of the energy flux, calling energy differences between different places on Earth. So like choosing these indexes, you can see the OAR contrast between the two regions from each model with a marker here. So GISS model had like 3.3 watts per square meter of differences between the two regions, comparing the peak and dip here. And the model ensemble gives us around 2 watts per square meter, and it's well correlated with the OAR differences between the two regions. Well correlated the tropospheric relative humidity differences between the two regions. So if we draw a regression curve between the OLR contrast and the humidity contrast between the two regions, I can get that the mid-tropospheric RH spread explain 89% of the spread in the OLR contrast. And now we can have a conclusion that like models that tends to have a stronger non-linearity, such as in GISS model, tends to have much stronger mid-tropospheric RH vibration over the tropical ocean. And yeah, so on the right, because I think explaining the curve is not enough, so I took every TS range into the right. So each dot represents one model at one surface temperature range, and I compare how much those models differs at a given surface temperature range. So you can, and again, I compare the difference, the inter-modal spreads in mid-tropospheric RH and draw a correlation between the two. So x-axis is the inter-modal spread in the mid-tropospheric RH among CMIP-6 models, and on the left as the spreads in clear sky OLR at the same surface temperature range. So so the spreads in mid-tropospheric RH explain 66% of the spread, and if one model have a moisture mid-troposphere, it is likely to have a lower clear sky OLR. So that's what this figure tells us. Then the next step is that we go back to CMIP-6 original output rather than use the RTMGP. So because this is the fluxes that are actually drive the model. So any differences between this figure and the previous figure reflects differences in radiation treatment. So now I think the GISS model becomes more of the outlier in this figure. So it produces an even more stronger contrast in the vibration in OLR over the tropical ocean. And then it tends to give a lower OLR compared to all the other models at the same surface temperature beam. So it really implies the differences in radiation treatment and how perhaps the land model produced a land surface temperature. So the take-home message in this section is that the vibration in mid-tropospheric RH really controls the OLR by altering the emission temperature of the atmosphere. It's not enough just to consider the entire moisture content held by the column. And also a message here is that the discrepancy in radiation treatment can also cause large OLR biases in one model. Do I have, yeah, so since I have some time left, I wanted to also to try to say something of how the OLR-Ts curve observed in present-day Earth are useful for climate projection. So the figure on the right are showing the clear sky OLR we computed using an offline line-by-line radiation plus the inputs from a coupled model run. So CTL as the control run, and ECS marks for the equilibrium climate state after 4 times CO2 experiment, and we run it for like 4,000 years, and using the input, the output from the ECS run, and then plus the offline line-by-line radio transfer, but then holding the CO2 content identical as the control to see how much OLR changes due to the state change in humidity and temperature. So what's interesting here is that basically the OLR-Ts curve in the black from the control run just shifted quite uniformly to a higher range, and the slope that we discussed a lot in this talk largely retains, and the peak over the tropical ocean also retains. We still have a peak in some warmer surface temperature range, and then a dip at the same distance away. So that's very interesting. I wanted to, link the view we used in this study to the conventional kernel-based feedback analysis. I'm not sure how many of you are familiar with that, but I wanna just to introduce that radiative kernel is a very simple tool. It pre-calculates the radiative sensitivity at the reference date for every grid point and every vertical level of Earth. And then, so Solony held 2006 proposed that we can use the pre-computed radiative kernel to assess the climate feedback of Earth. So so for the clear sky Longwave component, it only have 3 components. So one is the surface temperature. So it perturbs the surface temperature, run the calculation and see how much OLR changes. And this definition of surface temperature kernel is actually identical to the surface term that I used in this study for each grid point base. And then we also have other terms for atmospheric temperature and atmospheric water vapor, and those 2 terms are evaluated layer by layer. So once we have a climate model output, for a broad 4-time CO2 experiment, we know how much the surface temperature, atmospheric temperature, and water vapor changes exactly at every location. So we can times the actual perturbation with the radiative sensitivity and then regress it over the global mean surface temperature change and then evaluate how much feedback is caused by surface temperature, atmospheric temperature, and water vapor. And the sum of the 2 are the Longwave feedback that you see in the AR6 report of IPCC or some climate model sensitivity assessment. So the magnitude of the clear sky component of Longwave feedback is at -1.8. Simulus model has a really good agreement on that, and the global mean of this surface temperature feedback is -1.2, and the water vapor feedback is 1.6, and the air temperature, the feedback from air temperature is at -2.2. So there are very different ways of decomposing the sum of those, but now I just wanted to show, how much the magnitude of it if we don't consider the detail of analytic process that causing those vibration, but just focusing on the sum here. So on the plot here, I'm decomposing the feedback as a function of surface temperature. So the black curve shows the total, and the red curve shows the contribution from the surface temperature. On the right, I'm showing the contribution from water vapor and temperature. A very interesting feature that you see here is that the magnitude just tends to be compensating each other, and that's exactly the interesting feature observing Solon and Helm 2006. But what's important is that once we sum it up into the blue curve on the left, this term is not 0, and water vapor and temperature feedback does not fully cancel out each other. It doesn't cancel out each other, and it's very important because if you look at the curve in the total in black and the curve in blue, you can see that the shape of the total feedback in the surface temperature component coordinate is highly controlled by the atmospheric contribution. It means that it's really the vibration in the atmosphere that controls how large our climate sensitivity is in the Longwave part. So why we care so much of the temperature and water vapor doesn't sound to 0? Why is it so important? So if we go back to the Simpson's law, which claims that it actually developed to explain the climate sensitivity at the first place, but then we have a loop, in the discussion here. So if Simpson's law holds, then the clear sky Longwave feedback would be only controlled by the surface temperature feedback, which is just a weighted sum of the surface temperature kernel over a warming pattern, and the surface temperature kernel, the magnitude of it, is just shown on the plot on the right. So it's identical to existing data set for Longwave kernel. And the plot on the left in the red curve is just weighted average at each surface temperature being according to how much it warms in different regions. So the message here is that if Simpson's law is true, then the extreme moist tropical region without any moistening or additional effect, a runaway greenhouse effect would unconditionally occur, because in the earlier view, once the atmosphere becomes transparent, then no emission from the Earth can escape to outer space any longer. So that once there is an extra force in the climate system, we don't have any radiating mechanism to lose this extra energy to space. So we will end up into a runaway greenhouse, so that the Earth will become warmer and warmer without any stabilizing mechanism. But it is the pressure broadening effect that we discussed in this talk, that introducing a non-negative, non-zero atmospheric feedback process that stabilizes our climate. So the take-home message on the final session is just, this is an alternative way of understanding the clear sky Longwave feedback, and it's not so much different from the kernel-based analysis. And the pressure broadening effect is the reason why water vapor and temperature feedback does not fully compensate each other, and that we see in the existing studies. So yeah, that's the end.
Thank you. Okay, we have more than enough time for questions. We've got 7 minutes, so I'll just open it up to questions here. And then if you're online, you can unmute yourself and ask a question as well.
You mentioned you had a paper on this. I'd be happy to look it up, but I was curious if you could briefly talk about how you found out the value for beta equal 0 to 2.5.
Sure, I will try, but if I go too long, it's really possible, but yeah. So I'm not sure how much you are familiar with the spectroscopy. So here I'm just trying to show the the emission temperature change in the spectral view. So the top panel in blue shows if you have a kind of from control state to a equilibrium climate state, and then run a down-by-line rate transfer model, how much the total emission temperature changes. And the x-axis is the wave number. So it goes from 0 to 1,800 as the upper limit of the infrared spectrum. So so from 200 to 600 as the water vapor rotational channel. So in water vapor rotational channel, you can really just use the equation here. So it's really about how Clausius-Clapeyron relation controls the mass of water vapor, and also how much the pressure broadening effect affects the extinction efficiency of water vapor. And we can draw a simple equation and then solve an equation like this, and then we got that the emission temperature changes in the water vapor rotational channel is at 0.15 Kelvin. And then if the atmosphere doesn't have water vapor, it only constitutes of CO2 or other well-mixed greenhouse gases, we would expect the emission temperature just increase 1 Kelvin per surface warming, because it's well mixed. If the if we have a Planck-like uniform warming, surface warmed by 1 Kelvin, atmosphere warmed by 1 Kelvin, it means that the same CO2 is also heated by 1 Kelvin, so the emission temperature would increase by 1 Kelvin as well. So then it's just a matter of how this 0.15 Kelvin per 1 Kelvin of emission temperature caused by water vapor overlaps with CO2. So the actual curve by the atmosphere is drawn in the red line here. So you can see a much higher value in between 800 to 1000, and at 1200. This is the infrared window channel. So here it's really just like Planck feedback. So if you have 1 Kelvin increase, you have 1 Kelvin increase in the emission temperature. But then if you see like between 600 and 800, it has a mixture of water vapor absorption and CO2 absorption. So that gives a magnitude between 0.15 and 1 Kelvin, depending on how well the gases overlap. But so how we get the 0.25 is just an integral over the entire spectrum. So if we consider the broadband fluxes as a summation over the tiny spectrum, we get the 0.25.
Interesting. So you talk specifically about the rotational band. Does the vibrational rotational band not matter as much because there's no overlap with CO2? Or?
It matters as well. So you can see like 1,400, like 1,800. So it's also at around 0.15 Kelvin. So it's definitely helpful in dragging the value more closer to 0.15 rather than a higher.
Oh, rather than towards 1.
Yeah. So our climate is less stable than if we don't have the vibrational rotational channel.
Wonderful.
And it becomes more stable if we have more water vapor and if the absorption channels of water vapor are broader.
Wonderful. Thank you so much.
Yeah, I hope it doesn't bore you with the
No,
details.
that's very helpful. Thank you.
So it seems like conceptually what you're doing in your whole explanation in terms of emissivity depending on temperature and pressure, I mean, that's really something you can kind of do from the standpoint of a gray atmosphere.
Yeah.
Like, so I understand when you're doing the calculations, you actually have spectral resolution, but it seems like conceptually it's basically saying, the water vapor, like Simpson's rule, is dilated.
So so one thing I've been thinking is that what's the differences between a gray atmosphere is that gray atmosphere doesn't correctly simulate the pressure-broadening effect. So I suspect, but I don't have any evidence that if you have a gray radiation model that drives the climate of Earth, it will be easier to have a runaway effect because you lose part of the stability comes from the atmosphere. So that's my suspicion, but I don't run planetary model with simple radiation scheme. So, but I'm interested to check if there's any studies, and I think there are some important feedback process that could be important to the development of cyclones, because it matters of how much the radiative heating rate of the profile in a clear sky fraction of the Earth, which can feed back into the intensity of the storms. So, but yeah, this is just my suspicion. I don't have it. Yeah.
Sorry, I'm just going to interrupt for a second because we need to end the online meeting. So for those of you that are online, we're just going to end it here. But if people are free and want to continue discussing, we can keep discussing in person.